Okay. All right. So welcome everyone to the next seminar of our high energy theory seminar series. So today we are very happy to have Harold Erbin from IPHT CEA-Saclay telling us remotely about cubic string field theory using auxiliary fields. So Harold, please begin.
Hi, thanks a lot for the introduction and also for the invitation. So I'm very sorry to not be able to travel and meet you in person, but so if anyone wants to discuss more on this topic or anything else after the talk, don't hesitate to drop me an email and then we can make some discussion that we can do as if I was in person for getting more interactions. So in this seminar, I want to present some ongoing work on cubic string field theory. First, I would like to shout out to Atakan, so my collaborators on this project. So who is now a postdoc at UC Davis after doing his PhD at MIT. And so I will start with some general introduction and explaining why we want to get a cubic string field theory and why it's important. And then I will enter more in the details and see a few models.
Harold, excuse me.
Yes.
I think we are not seeing the entirety of your screen. Probably
Okay. Let me try something. Is it better now?
It might be, not really sure.
Yeah.
If you go to the second slide, if you go to the second one.
Yeah.
Now I think we can see.
Yeah, but it's okay. Let me do something. I was trying a new feature of Zoom, but apparently, can you see everything now?
So we see just three bullet points, and here too.
Okay, so let me stop sharing, and I will try to share again.
Okay. Yes, that's much better.
Okay, yeah, sorry. Yeah, I apologize for this technical. I was trying to use a dual monitor mode of Zoom and it doesn't work so well. So, okay, so I'm showing again the nice picture of Atakan, so my collaborators on this topics within UC Davis. Okay, so I will start with some general motivations. So first, a few words on string field theories, and I will come back later for like introduction with more details and more in depth. But here I just want to give like the main ideas of what is string field theory and how we can think about it and why it's difficult to work with. So you can really see string field theory as a standard QFT, which has an infinite number of fields of all spins, which is non-polynomial. By non-polynomial, we mean that there is an infinite number of interactions. It's also non-local, so interaction will be typically of this exponential of minus k square form. So in particular, it diverge in Lorentzian signature when for energy is going to infinity. And we want this string field theory to reproduce the worldsheet amplitude when they are well defined. And if the worldsheet amplitude are not well defined, string field theory should provide a regularization and proper computation of those amplitudes. So I think this way of thinking about string field theory as a normal QFT is very nice in its particularly interesting features of this formulation, because then you can just bring everything you know from QFT and just apply it to string theory instead of trying to work with Riemann surface and so on. You can already try to get some insight just from plain QFT. So the problem, so as I said, we have an infinite number of interactions. So here you can compare this, for example, to the case of general relativity. So if you try to expand the Einstein-Hilbert action with a metric on some background metric, so the action will have an infinite number of terms in H. And what you see in string theory, it's exactly that. So you can really think as string theory as something expanding around the background. So you will get infinite number of contributions, which makes it difficult to deal with. And the second problem that we don't know this interaction except for the first few orders. So you cannot re-extract numbers or anything with string field theory. So here is the action of string theory. So first, I have some string field psi which live in the CFT Hilbert space. And again, I will give more details later here. I just want to show a few formulas to we go straight to the difficult point. And as you see, the action has a kinetic term, so it's quadratic in psi. And then you have an infinite number of interaction Vn. So Vn is just something which takes n fields and gives you a C number. Or you can see it also taking n states and giving you a number. So if you want to think about this, it's also like what gives you the vertices in the Feynman rules. So this gives you the propagator. This is the vertices, and so you can just write Feynman diagrams like you would do in normal QFT. Okay. So I will explain also more later, but you have something called the L infinity homotopy algebra, which gives you constraints on this Vn. And in particular, from this, you can show that this action is gauge invariant. So as I was saying, we don't know the Vn greater than 6 explicitly. And for n equal 4 and 5, we know them only numerically. So there's some very old work from Maurer doing it. And more recently, with Atakan, we did the construction of V4 using machine learning. So the consequence of this are that we can do very few explicit computation for a generic string field theory. Low-order truncations in terms of the field and interaction are not reliable because we throw away too much information. And we cannot answer major questions, for example, to know what is the closed string tachyon vacuum, if it exists at all. So you see, it's very difficult to re-extract information. I mean, precise information where you really need the number, like where is the vacuum, what is the depth, and these kind of things. On the other hand, what you can do is that you know the general structure of string field theory, so you can always try to like study general properties which don't depend on the fine-grained detail. So a bit in the spirit of the S-matrix bootstrap from the 60s. Okay. So despite these issues, there is like a miracle for the bosonic open string because we have one parametrization which has only cubic interactions. So it was found by Witten in 86. So in this case, so we have the kinetic term again, and then you see that you have a cubic term and nothing more. So it's cubic, it truncates. And because it's so easy, especially because the cubic vertex in string field theory is really easy to understand, you can do basically whatever you want with that theory. So you can find analytic and very truncated solutions of many different types. So you can study tachyon condensation, brain decay, time-dependent background, and so on. You can compute effective actions, and you can do many more things. So here it's really like a theory where you can do computation explicitly. So the question is that can we find a cubic closed string field theory? So first bosonic, but also then later also superstring field theory. So now I want to introduce few theorems. So first we have a no-go theorem from Sonoda and Zwiebach in 19, which says that there is no covariance covering of M04. So M04 is a moduli space of Riemann surface with 4 punctures. So it means that it corresponds to 4-point amplitudes, assuming a symmetric cubic vertex, standard propagator, and BRST invariance. So in other words, it tells you that you need a quartic vertex to describe this amplitude in string theory. Okay, so it's kind of a no-go, and since that time, people thought that it's impossible to find a cubic closed string field theory because if you want BRST invariance, this you don't want to give up. And the other thing, it's a bit hard to see what you can do instead. Now you have a second theorem which started to get better known recently, which is a strictification theorem, which says that any homotopy algebra is quasi-homorphic to a differential graded algebra. In words, it tells you that you can always find a parametrization where all the Vn with n greater than 4 or equal are 0. Now you will tell me, okay, there is some kind of tension between these two theorems because one tells you can set V4 to 0 and the other tells you can't. So why is so? So way out is to use the auxiliary field to decompose interactions. So the first way to do it is to use the Hubbard-Stratonovich transformation, which comes from condensed matter. And the second is to embed this in the homotopy algebra formalism by introducing a IBA infinity structure. So why auxiliary field help to address this problem, and why we can evade the theorem, the first theorem. So the first is that point is that we enlarge the Hilbert space by having more fields. So because in the two theorem, what we don't say in the assumption is what is the Hilbert space. And the point that the Hilbert space for the two theorems don't need to be the same. So it means that in one case, you can have more structure. So it's really important to know what we mean, because at the end, what we care for string theory is like the on-shell scattering amplitudes and the states. So if you have two theories which are off-shell and have different things, but on-shell they give the same results, basically they are the same theory with different parameterization. So the second theorem is telling you there should be a new parameterization in some new Hilbert space where you can write everything cubic. Also, when you start to have more fields, you get a non-symmetric vertex, and you also get a non-standard propagator. So here we see that we can violate two of the assumptions of the first theorem. Okay, so here was the introduction to set up the stage. Now, so for the talk, so I will move to a general introduction to string field theory. Then I will explain this, how this works for 5-4 scalar fields. Then I will apply this to open string field theory with stubs. So this is an action which is non-polynomial, but still simpler than closed string field theory, so it's also a good toy model. And then I will give some speculation about what we can do with closed string field theory. Okay, is there any question at this stage? Okay, so if not, I will move to introduction to string field theory. So in string theory, the usual formulation is based on the worksheet. So the worksheet is the first quantized theory. So you can think of it as we studying the dynamics of a few strings. But if you want to ask what happens when I have many strings, it starts to get complicated. You also have various problems like it's on-shell, it's perturbative, and so on, because it's the first quantized theory. So you have some limitations, which we want to address by removing this first quantized constraint. Before going there, I want to mention that an amplitude in the worksheet theory is represented as a correction function in a 2D CFT, which you integrate over the moduli space of a Riemann surface. And we'll see why it's important just after. So string field theory is a second quantization of this theory. And in some sense, it's really like what people did in the old days. So we had quantum mechanics. We studied the relativistic version, and we had first quantized theory. Then people did the second quantization by saying that the fields become operators. Now the way we do QFT is more modern, is that we directly start by the action, start with the fields which satisfy some, which live in some representation of some group and so on. So we build the QFT from first principle. In string field theory, we're still not exactly there, because why we can do this for the general structure, if you want to compute something, you have to go back to this second quantization where you see everything as operators coming from the first quantized version. So here it's one limitation, but despite this, we can still access many more things, like all the tools of field theory. It's also more constructive, and you make the symmetries manifest, so it's definitely a bonus over the worksheet theory. You can use this knowledge of the general structure and of the symmetries to prove consistency, so you can do exactly like people did for the S-matrix analysis and so on, so to prove unitarity, analyticity, finiteness, and so on. You can study backgrounds, so like background independence, what happens if you have flux, if you want to find classical solutions and expand around them. So you will have a world which is open to you with string field theory. To go back again and stress these points, we have this problem that it's non-local, non-polynomial, and we have infinite number of fields. So we need a way to reduce this complexity. And then general properties are known, but not the explicit form. So again, if in any way you can find a way to characterize the interaction in string field theory, it's good to move forward. So here is a small diagram to make this summary of how we go from like the on-shell worksheet theory to string field theory, and what is the relation to the geometrical aspect. So in string theory, you will have two sides. So you have the geometrical side of Riemann surface and moduli space, and you have the QFT side. The geometrical side is background independent, so anything you define there will work for any background, any string theory, and you can reuse it in every cases. So at the origin, if you start just with the moduli space of Riemann surface, you can use the 2D CFT as a map to associate to this plus a background defined by this 2D CFT, a string amplitude. Okay? Now, if you take this Riemann surface and you add some additional data, which correspond to local coordinates on the puncture, so you can imagine that so the Riemann surface is really, something with like holes, and then you have marked points. So the marked points correspond to where you insert the strings. So now if you add local patches of coordinates on those points, this gives you a way to move off shell. So again, now the 2D CFT gives you a map from this moduli space of Riemann surface and local coordinates to off-shell string amplitudes. Now, if you take this Riemann surface, so the moduli space, and you use a decomposition by steering. So by steering, we mean let's take two surfaces, glue them together, and you get a new surface with like the sum of punctures of the two previous surfaces. You get a new surface. You can do this for all surfaces, so you will see that you induce a decomposition of the moduli space. This decomposition, you can associate something which is called the geometric BV algebra. Now, if you use the CFT to map this again to the physical information, you get a string field theory, which also satisfies the quantum BV equation. So this tells you that because of this background independent geometrical information, you get a theory which is well defined at the quantum level. So no anomalies, it's gauge invariant, everything you want, thanks to this 2D CFT, which you can also show is the BV morphism. So it's a map between two BV algebra. So this is something very powerful. And so a big deal of string field theory is understanding how to build this data here. So in our last paper with ATACAD, it's what we did using machine learning. But we have other ways to try to attack this problem here of understanding the geometry. Because once it's done, the geometry, you can just do apply it to any string theory you want, so bosonic, closed string, superstring, and so on. So here are some pictures of what I mean. So when we have, so first a Riemann surface like this, as you see, we have, so it's a two-loop, so it's a surface which contribute to a two-loop amplitudes. And we have 2 points, so this would be a two-loop contribution to the propagator. Okay, so now on each punctures, I will introduce some patch of coordinates, which I map here to the unit circle on the plane. And so the information about this blue map and the red map allows me to go off shell. Now, what is showing? So I can split my surface in 2 types. So I have the types which I will want to call a fundamental vertex. So it's when I have all the strings interacting together in a small region of spacetime. So because it's string, it's not a point, but it's more like diffused. And then I have some graphs where I can interpret as like 2 strings coming together, creating a new string which propagates for some time, and then this string decay into strings, for example, like here. So I have these 2 types of graphs, and it's telling you that you can decompose the moduli space in different regions where you have a vertex region, so where you just get graphs of this form here, and propagator region where you have graph of this form. And now the point that from this data about the propagator and the vertices, you can build string field theory. So how we do that? So as I said, the string background is defined by a 2D CFT. So for example, if you just take D free scalar fields, you get a D dimensional Minkowski space. So we know that for bosonic strings, because of the anomaly, we need D equal 26, but you could add other fields and get a more complicated background. The string field, psi, lives in the first quantized CFT Hilbert space, so built from this theory. And the classical action, as I showed earlier, has this form. So we have a quadratic term for psi, and then we have all this interaction of order n. we have QB is the BST operators. And you can again see the string vertices as contact interaction, where by contact we mean occurring in a small region of space-time. Now what we need later is also to introduce this Ln operator, which are called the string product. So a string product will take n states and give you another state. Okay, so we will see why they are important. And now you can write the equation of motion, so you can just take the variation. You see that you get QB psi plus the sum over all the string products. So you see that for GS equals 0, you just get QB psi equals 0, so it tells you that the physical states are in the BRST cohomology. And then you get more and more interactions. So for example, you can try to solve this iteratively and so on. So now we have something which is called a homotopy algebra, which is a extension of real algebra to more complicated case. And this homotopy algebra can be used to show that you have a gauge invariance of the action given by this transformation. So you see that you have a parameter lambda, which is also a string field. And the L infinity relation has this form. So overall, you take you fix some n, so you have one relation for each n, and you basically take the commutator in some sense of all the possible string products where k plus L is n. So to fix the ideas, here are some examples. So the first one is like for n equal 2. So you see that k equal L equal 1. No, sorry. K is 0, L is 1, and n is 1. So then you get q squared applied on any state is 0. So it's telling you that BRST operator should be nilpotent as it should. Second relation, so for k plus L equal 2. So you see that you have one case where k is 1 and L is 2. And k is 1 and L is 1. So here what you get is that you get QB of L2 plus L2 of QB, and then the permutation. So what does it mean? So L2, you should really see it as a Lie bracket. So here it's telling you that QB is a derivation for the Lie bracket. Okay. So here, by these two, if you just add these two relations, you would have a differential graded algebra. So you can really think of this as a real algebra where operators depend on T, and so the derivation d over dt just acts as you would expect on matrices, for example. Now the third relation is more interesting. So you have QB acting on X3. So X3 is a three product. So you take three states and you spit out one. So if you apply QB on this, you will get then L3 of QB and you have the permutations. But this is not 0. It's equal to L2 inside which you use another L2. So if this, you write it in terms of a Lie bracket, this second line would be the Jacobi identity. So here what it's telling you is that the failure of the Jacobi identity is explained by the presence of these three, the string product with n equals 3. And QB is not a derivation of this new product up to the Jacobi identity. So you have a relation like this kind of relation. So you have Jacobi, it fails because you need to have a new product. Now this product, it will intervene at higher orders, and some properties which generalize the Jacobi identity will fail up to similar terms of QB being a derivation of higher order product and so on. So you have this tower of identities, which is used a lot to compute in string field theory. So, okay, I think I need to speed up a bit. So now if we want to compute more explicitly and try to understand this in terms of a QFT, we can do a Fourier expansion. So in some sense, we have a double Fourier expansion. So we have a Fourier expansion for the center of mass K, so which gives you the momentum. And then you have also a Fourier expansion given by the finite size of the string, which will give you some indices A, which can also come from other properties of the CFT you choose. So A can be Lorentz indices, group representation, KK modes, and so on. And for the 1p action, we have this form. So you have a quadratic kinetic term here. And then you have an infinite number of interactions which are characterized by these vertices, vertex functions, so which depend on this A and on the momentum K. So one way to try to compute with string theory to just start with this section and ask, what can I do with this general form, even if I don't know the details? And I will show later how this works using scalar fields to get inspiration. Okay, so here is the general form of the operator. So you see you have the inverse of Kern-Gordon, a mixing matrix for the mass, and then some polynomial in terms of the momentum. You have the vertices. So here the form is not important, but you can really see it as an exponential of k squared, as we saw from the non-locality of the string. A regularization term for the mass, and here some polynomial which depend on the momentum with various contractions. Okay, so now here we are using a language which is a bit different from string theory, which is because we have a second quantized theory and not like a proper full-fledged QFT. So let's take the action for a quartic scalar field written in this form. So here it's really just a phi 4 with phi x to the 4. We want to rewrite this first in momentum space and then in the string field theory language. So in string field theory, we would write it like this. So we have some inner product, some operator k, and then we have a quartic vertex operator, which will take these 4 fields and gives you a number. So first, we have the state phi. So phi is not the field here, but it's really a state, a first quantized states, and we want to explain it over a basis for that states. So natural basis of the plane wave. So I will write phi as phi k sum over k with a k given by this basis. And so how we define the inner product, we just say that two plane wave orthogonal except if k equal k prime. Okay. K, we take the Kern-Gordon operator, so you can see that it will act like it should on this state here to reproduce the first term. And then the quartic vertex is just defined by this integral, and here the quartic function is just the delta function. So as you see, it's kind of it's just complicated way to rewrite everything, but at the end, it's really a one-to-one mapping to normal QFT. Okay, so here I say it already. I just want to mention that why it's difficult to get this Vn in string field theory. It's because for each n, you need to find n holomorphic functions, which satisfy some constraints. You also need to find a specific subspace Vn of the moduli space M0n. And you need to make sure that when you glue all that subspace together using gluing, which is like building Feynman graph with propagators, you need to get a single covering of M0n, which also respect gauge invariant. So this is very challenging. So we need to find ways around this. So as I said, we can still understand general properties and prove consistency of string theory in this way. And recently, there are many progress on various aspects of string theory, and I recommend this review from Sonoda and Zwiebach about it. Okay. Before going to the first toy model of phi 4, is there any question?
May I ask a question?
Yes.
So you said this is similar to QFT. So is this the case that you have annihilation creation operators and a linear combination of them, or you can have any other polynomial?
Yeah, so it's very similar in the sense that when you write the field, sorry, here, so that's phi a of k, or like normal field you get in QFT. So normally it would be like scalar field, vector field, and so on. So now we think of them as in the path integral formalism, so it's why we just write a field, but you could promote them to operators, and then you would get creation and annihilation operator. The main problem is that string field theory is not really well defined in the operator formalism. So you can do it in light cone. So there are some old papers, but the argument is that it doesn't work well, the operator formalism in string field theory. So in general, people will stick to the path integral, but we have like philosophically, this phi L could be annihilator and annihilation and creation operator.
Okay, thank you.
Do I have more questions? Okay, so if not, I will move to the 5-4 theory. So first, I want to review some general idea about Hubbard-Stratonovich representation. So originally it appeared in many body physics, and the goal was to decompose interaction into lower order interactions for auxiliary fields. But it's not the only features of this. It's not just you get something simpler in terms of the order, but you can do even more. So the optimal representation, which you get from Hubbard-Stratonovich, has only cubic interactions. It's quadratic in the physical fields and linear in the auxiliary field. So then it's very interesting because first, so the auxiliary field, you can interpret them as order parameters. So for example, if you just get phi4, the auxiliary field sigma, so if you set it to constant, you reproduce mean field theory where sigma is a magnetization parameter. So now if you integrate out the physical field, you will get an effective theory for this order parameter plus fluctuation of this order parameter. So in fact, you can try to access also like thermal properties of your theory. So it's interesting for us in string field theory because if we manage to get this kind of auxiliary field, then the next step is to ask, okay, what can I do like people do in condensed matter? Can I study condensed state of strings and so on? The second thing you can try to do is to integrate out or find consistent truncation of a subset of auxiliary fields, which was, for example, exemplified in this paper. So imagine you want to solve equation of motions. If you just work with a closed-string field and you want to expand in terms of field, you will get an infinite number of fields and interactions, fields in space-time sense. Now, if you have auxiliary fields, you can hope that if you just set some of the auxiliary field to 0 in a consistent way, you will just reduce to a lower number of interaction with which could be easier to solve. In fact, it's a bit what people do in open string, because when you find an analytic solution, in fact, you just truncate the states you want to look at. So you look at a smaller subset of states, and then you solve this. So it's called the KBC algebra. So here, the idea would be to do something similar, but using this auxiliary field. Okay, so here is the action for the 5-4 scalar model, so with some arbitrary kinetic operators. And we want to introduce an auxiliary field sigma, which is equal to phi square on shell. So now if we write this Hubbard-Stratonovich action, we see that sigma, so if we take the version with respect to sigma, we find indeed sigma equals phi square. And if we plug back this, we go back to the previous action. So on shell, it's completely equivalent. Sigma is not dynamical because there is no k here. So it's really just a plain auxiliary field. But the good point is that now you just have cubic interactions. And how it works in terms of N-Mahan diagram, so it's a very simple exercise. So you see that this quartic vertex, which you had before with a strength lambda, now it's reproduced by this graph here, where you have two phi fields coming together, you have a sigma propagating, and again, two phi. It works because of strength of the interaction is lambda. Propagators come with 1 over lambda. So altogether, you just get 1 lambda. You will get a factor of 3, but you have STU channel, so it compensates, so you can recover exactly this diagram. Okay, so here it's really the simple things to exemplify, but it's too simple for understanding what you should do in string field theory. Like you need some more scalar field and something more complicated to try to get some insights. So a vector model is a 5-4 vector model. Okay, here it's a typo, it should be I. So you take n fields, and now the interaction, so it's local in X, but you have a general interaction for tensor here. So obviously it's fully symmetric. You can see it as defining some symmetric matrix. So this matrix is invertible. Because in general, we assume there is no eigenvalue, because if you have an eigenvalue, it means you have a basis where some of the phi decouple, so we don't care, it's not relevant. So what we can do is to introduce of the order n square auxiliary field sigma ij to cancel the quartic term. So now you can say, like, when you look at this action, okay, like, how should I write, which term should I add to the action? And so there is a very nice trick from Weinberg in volume 2, where he says, okay, add this term in the action. So basically you just take V, the V tensor, and you replace 2 phi by sigma minus phi phi, and you do it twice. So because you see that when you expand, you will get v phi 4. So this v phi 4 we cancel the term here, and then you just check what remains. The equation of motion is again telling you that sigma j is like a condensate of phi j. And the action you get at the end is the following one. So you get v sigma I sigma square and a v sigma phi phi. So it's cubic. Sigma is indeed doesn't have a dependent in no derivative in the kinetic term, so it's auxiliary. So you get what you want. And now, if you look at the form I had shown for the 1p action of string theory, you have something which is of the form of the previous slides. So now it's kind of giving you a hint that you can try to use the same trick in string theory. Also, I want to mention that you can reach the same action for more general actions. So, for example, if you work in momentum space and you work with a general interaction here where v depends on the 4 momenta and each phi is inserted in different momenta, K1 to K4, you can still play the same trick. You can still reach this action, but now it's not clear how you continue to work because V has a momentum dependence, so you need to make sure that it has no 0 for the sigma, otherwise sigma would become dynamical. So you start to have a few constraints here which are still not clear how you deal. Also, sigma would in general be bilocal in momenta, so it's also more complicated. But okay, at least you can reach this stage, and interpretation we can think later. In terms of Feynman diagram, we have something like this. So this V for tensor, you can see that it's equal to this. So where here you propagate 2 indices at the same time, and you can invert this for tensor in the sense of matrices. And that's all. So here it's really like the inspiration for going to string theory. Is there any question at that stage? Okay, then I will move to open string theory with stubs. So what is a stub? So the stub is a proper time cutoff. So you can imagine that if you work with a Schwinger parametrization, you just cut off the short proper time propagation from where you get all the UV divergences. Another way to see this is to, it means that you're reshuffling what you call propagator and what you call interaction, as I will show just after. Now the point that the open SFT with stubs is non-polynomial, because in fact, like even open bosonic string theory in general is non-polynomial. It's really just if you work with Witten's parametrization that it's cubic. Okay, so basically any open SFT which is non-Witten is a good toy model for closed string theory. But the point that the one with stubs is really the simplest you can get. So it's really the best place to start and see if you can make it cubic again using the tricks we have seen before. So here are some references. Okay, so I write again the action of open string theory in single gauge. So here we see that we have the kinetic term. Here we have the cubic vertex, and here I have written it explicitly in terms of this non-commutative product. We don't need to know the details for what it means. You can just see it as kind of a matrix product between these two phi. Now the propagator looks like this. So if you need to invert this operator, so the inverse of C0 is B0, and it works because you're in single gauge, so you know that it's well defined. And the inverse of L0 is just 1 over L0. So it's not so convenient to work in this form. Here so we introduce a Schwinger parametrization where you have this S, which is with the proper time. And this form is also nice to make contact with the worksheet formalism, because the worksheet will give you the right-hand side here. So in worksheet, what you do is that first you need to find this expression, and then you can represent by QFT propagators, which you can see as an analytic continuation. Okay. So now I'm introducing a cutoff on the short proper time. So I will have this regularized propagator delta of lambda. If you perform the integral, you get something like this. So you see that you have a dumping for large X0 eigenstates. We can also introduce a pseudo mass parameter by the remaining of the integrals. I call this a mass because I will see it behaves like a mass and it doesn't contain so this m square never vanishes. So it just, anything with this parameter is not dynamical. And I will introduce the lambda projector. So it's not real projectors, but it's for all like practical purpose, it behaves like a projectors. And if you take lambda to infinity, you get the on-shape projector. So I will just call it a projector, even if it's not real projector. And now, so let's see at how you write the action with stubs and how you do. So let's take.
Can I ask a quick question?
Sure.
So so when you put the cutoff of 2 lambda on your kind of your propagators, right? You're integrating out the propagators with length of less than 2 lambda, and then moving them to the interaction vertices, right? When you're integrating over the space. So,
yes.
So I saw some discussion about it maybe being equivalent to like effective field theory and moving up in mass, but is that a good way to think of it? Because in the closed string field theory with the minimal area stuff with the pi length, I mean that seems like it could cover the whole space just with that. But should I think of it as integrating out modes like?
Yes. Indeed, you have different ways to think about it. So you can see it so as a cutoff, indeed. Now this cutoff, it will correspond to RG scale for the Polchinski equation. So if you write the classical action in terms of this lambda, you will find that it satisfies the Polchinski equation. So as a running scale. Now we know that Polchinski equation is with the interpretation is something where you have a soft cutoff and you have some fast modes, some slow modes, and you integrate out the fast modes and you get the low energy action. So here you can also see this lambda as like moving, like integrating out in an effective manner like high energy mode of strings. But because like the string is really kind of a continuous state, you are not really removing like state by themselves. You're just making states with very high I0 quite improbable to appear in this effective theory. And the point, as you say, is that string field theory, in some sense, always has a stub parameter. You can show that you need a minimal stub parameter for the theory to make sense. For minimal area, it's related to this pi parameter you were saying. So you will always have a stub. And indeed, when you move it, you will find that the vertex area is changing. And one question is, okay, if I take some limit, do this area shrink to 0 so that I just get like cubic vertices? And the point that you can show that it's not possible to just play with stubs to do that. One of the reasons is that then so it will not like shrink to 0, but it will do it in a way like if you want to remove all the vertex region, in fact, you will start to overlap again with the propagator region, so you have double counting. So then you need something to compensate for that, which will be effectively a new vertex.
Okay.
Is it clear?
Yeah, that helps. Thanks.
And John, just a fun fact of this lambda also. So it also appears in neural networks. So you can associate an effective QFT to neural networks. And you can show that this something similar to this lambda appears in the to characterize the initial distribution of the neural network weights. And you can also define the RG flow, which is formally the same as you get in string field theory for neural networks. So it's a small fun fact. Okay, let's go back to this. So here it's related to the discussion we just had. So in principle, you have this quartic diagram with some propagator of here. So this S will take all values from 0 to infinity. But now I want to say, okay, hold on. I don't want to take into account the small proper time propagation. And I will say that my propagator is this. So propagator is really anything which has proper time bigger than this 2 lambda. So I will have also this contribution for S smaller than 2 lambda. But for currently, there is nothing to account for this contribution. So in practice, I will collapse this and just define an effective interaction. And you see that, okay, here it's something you can do also with normal like QFT and scalar fields. And it's made really like string field theory because you say, okay, something which happens at a size less than 2 lambda in spacetime in some sense. I don't want to be able to resolve it, so we just put this in some effective interaction. And this interaction, in fact, will be non-local because we're looking at a small region of spacetime, but not a point. So even-square field with stub is a very good toy model for string field theory because you will find many features there. So we need to define this effective vertex, so which I call here V4 tilde of S. And as you see, just every diagrams you get where you integrate this S less than 2 lambda. Sorry for the typo here. Okay, so now if you rewrite your action in this way and you rescale phi by the projector just to get a canonically normalized kinetic term, you get something. So here you have this the same kinetic term as before. Here you have again the cubic term, but now each phi has a p lambda, which tells you that modes which with high L0 are really dumped done. And now you have a quartic interaction which corresponds to these diagrams that we cannot cover because we have excluded these short proper time things. So now the question is, and then you have infinite number of terms similar like this. And basically you can see this quartic and more terms built by taking, so you just take the generating function from normal QFT, but instead of using the Crane-Gordon propagator, you use this m lambda minus 2 propagator and you will just generate all the graphs. Because clearly this is built from all the graph where you have this kind of propagator, but from it still propagator. So it's how you can enumerate all the graph. So now the question is that can we introduce auxiliary field to remove this? I mean to make this quartic. So we do the trick from Weinberg. So we add this term. Okay, so now there is some factors which you need to shuffle, and after a few trials and errors, you find that this is the best way to do the transformation. You plug back, and now you find, okay, still the quadratic term. You find a quadratic term for sigma, cubic term for phi still, and now you have a cubic term sigma phi phi. Looks good. You can try to iterate. I have a quintic term here. Can I find a way to reduce this term? Yes. In fact, I can reduce also the sixtic. And now the magic of the stub is that, in fact, you can just stop there. Because if you write this action with auxiliary field where you have terms which are cubic in sigma, and then you have sigma phi phi and phi sigma sigma, in fact, by integrating out sigma, you will regenerate this series. The reason is simple. It's because in some sense, you want two fields, one which propagates the slow modes, one which propagates the fast modes. And here we go back to the previous question. In some sense, sigma will represent these fields with a high I0, which you have integrated out. Because you have integrated out, you get something in a local. Now you put them back, but you still split them from phi because you want to show that you have the kind of low energy physical fields, and then just the fast modes, but which are kind of non-physical, I mean off-shell. So you want to trade them on two different footing. Okay, so we have different type of vertices. We can also generalize this to any A infinity or L infinity action to remove the stub. So here I'm not saying that you can remove the non-polynomiality of the action, but if you have an action where you have some stubs, you can use this trick to remove the stubs. Or if you want to generalize the action with stubs, in fact, you can do the opposite and add stubs like this. So it's really like, in fact, opening new ways to compute with general action in string field theory. So here we are coming back to some comments I made before. In particular, you can also see stubs as regularizing the BV Laplacian. So it's also a nice way to understand this BV quantum master equation. Is there any question?
It makes sense that if you integrate out the auxiliary field, you get the normal theory. But what's the intuition behind the other way around? It's a bit strange to get. I saw in the thing that it was you get the cubic action, right? If you integrate out the field and leave the auxiliary field. But wouldn't you kind of expect like a freely propagating auxiliary field?
Yeah, okay, so the auxiliary field should not be free propagating because you really want to remove, in fact, the physical states. So at the level of the get fixed action, you don't need to remove it because of this, like it's just finite. but we see that for the gauge invariant action, you need to remove them. Now, okay, so let me get it right. So you're asking like if we could also integrate out the 5 fields and get something for sigma, right?
Yeah.
Yes. So you could also do it. And then what you would see something that like, I mean, phi and sigma, we apply the dual. So if you integrate out 1, you get an action which looks a lot, I mean, for the 2 up to some rescaling. It's normal because like the 2 will contain the same degrees of freedom, but with different L0. So if you integrate out phi, you will get a sigma, but in a dual kind of dual formulation, where you're expanding on the high energy modes, which would make the theory look a bit ugly, but it would just tell you, okay, you should in fact have done the opposite in some sense. But it's true that it could be a way to try to access maybe some information from high energy modes or something. And I have a comment a bit later about the different action you can do. I think it will be on this slide just after. So before going there, so I wanted to comment on the removing the gauge fixing. So here we have this term M2 lambda, and so we want to ask by what we should replace it to make the kinetic term here for sigma gauge invariant. So the simplest guess is to just replace the C0 L0 by QB, because it's what we were doing for the normal open string. And then we keep that term, and now in this form, we see that this term can have some problem when L0 equals 0, so we need to remove this from the auxiliary field state. We have a gauge symmetry, so here the brackets is like the bracket given in term, so it's like the real bracket, but for the star product. And so related to the one we're discussing, you can solve different linear combination of equation of motion to integrate out sigma or phi. So if you solve the equation of motion for sigma, you just get the original action for stubs as you would expect. Now you can also solve this peculiar combination. And here it's telling you that sigma is proportional to phi with this factor here. And now if you plug this in the action, you find that the auxiliary field action with sigma replaced by that, it's just the Witten action with an additional p lambda insertion. Sorry for the typo. So this you can just rescale the field and go back to the original cubic action. So it's kind of showing you that even if you started from the stub action, you could go back to the cubic action even if you didn't know it using this trick. Now, if you do it and you integrate out phi, in fact, you get the same thing with another prefactor here, but it's the same. It's just we're showing that sigma and phi are dual. You can also rewrite everything in terms of vector homotopy algebra. So by vector, I mean that the A infinity will act on the tensor sum of 2 operators. So we have an action of this form. So you see that it really looks like the original Witten theory. We have the fields which are packaged in 2 vectors. We have a bilinear form, so where we need this additional factor here for normalization. And we can introduce also 2 products. So we have a generation of the QB operator, which act on both states. And we have the 2 products, which is defined in this way. So we know that we have an infinity, so the theory is consistent. And it also gives some good insight about what we can try to do for the clustering. I guess that I just have 5 minutes left, right? So do I have 5 minutes or a bit more?
Yeah, you can go for a bit longer, for sure.
Okay, thanks. Okay, so now we move to closed string field theory because it's really like the big goal of what we want to achieve. And I want to show some examples. So one parameterization, which is the simplest, is this SL2C parameterization. So recently we had a long paper with Manjumbar explaining all the details about this vertex, but you can also find a basic introduction in the first volume of Poshinsky. So here you see that you split the moduli space of the 4-point sphere in the 4 different regions. So you have 3 Feynman regions, which are given by the STU channel. So you take the 2 cubic vertex. you join them by the propagator, and because everything is symmetric, you have 3 different possibilities. So the STU we have in normal QFT. So now if you look at which values of the moduli you get by this way, you would get this region which are left in white. Okay. Now something remains. So again, remember that the quartic amplitude in string theory is defined by integrating over the full moduli space. So you need to consider the moduli living in all these points of the plane. So this is missing. So we are forced to say, okay, to introduce this quartic vertex in the action to compensate. Now, if you add stubs, so what we do stubs? So the stubs will like shrink or expand outwards the circles here, and it will do the convert to the outer one. So for example, if you increase the stub parameter, so it means you reduce the contribution from the propagator, U and T would shrink, and the outer circle, ellipse, would expand. Okay, and now you can try to play with this stub parameter, and you will find that there is one place where here it will start to touch, but you cannot cover everything that way. Another parameterization, so the minimal area. So here it's what we got using neural networks. So here we train the neural networks to classify points in moduli space. Red tells that it's probability 1 to be in the vertex region. Blue, it's 0. And white is 0.5. So as you see, it's giving you the boundary. And here we all, like this minimal area parameterization is with a critical point. Where we see that this region will touch here at one point. So now if you try to change the stub parameter, either you would shrink the blue region, or you would just start to overlap. So again, you are forced to get the V4. And this explanation will come from this no-go theorem from Sonoda and Zwiebach. Okay, so to continue, let's write the action to quartic order. So we see we have the cubic and quartic vertices. V2 here is a BST operator. I'm introducing an auxiliary field using the trick from Weinberg again. And I get this Hubbard-Stratonovich action, which looks cubic because I just have sigma times sigma. And here I have a sigma psi square. Okay. And now let me note that here we start the wild speculations. So maybe what I say after is wrong. Don't shout at me. It just like trying to generalize what we saw in the previous sections. So the first thing you can note, which is a bit peculiar here, is that when we work with the open string field, the auxiliary field was also just a normal string field. Now here we see that sigma must live in 2 copies of the Hilbert space. In fact, it's exactly what we had seen for the vector scalar field, where sigma had 2 indices, I and j. So here it's why this vector model is a good toy model for closed-string field theory, because we have a bit this double, like this double copy of the Hilbert space. Okay, so it needs also that we need to introduce a new product, which will go from 2 copies of the Hilbert space to 2 copies. So we write this V4 as something like this. So we introduce some M2. And you can also define M2 from this X3 we had before. So at this stage, this is perfectly well defined. You can show that it works. So if you continue, you will get what we call surface states. So here, okay, no speculation. You get some equation of motion. So if you vary with respect to psi and sigma. And there you see that here you get M2 of sigma equal M2 of psi square. So in principle, the vertices in string field theory are well defined and you have no divergence because otherwise you will get some weird behavior for the amplitudes. So for me, it looks like it's possible to take the inverse of M2, but I didn't manage to prove it rigorously and so on. So for now, I'm leaving it in this form, but in mind telling you that sigma is really psi tensor psi. Again, like you find for the vector model. You have some gauge invariance for me. So again, it's a bit weird gauge invariance, but for me, it looks like it works. You can also do a Fourier expansion and you see that you get entangled sets. So you have this sigma rs, k1, k2, and here you have two states of your basis. So you see that you cannot bring them together. Sorry, you can you cannot split the field because like the coefficient really is bilocal in spacetime and in the indices. So what should we do? So first, let me note that the action is still not really cubic because the fields appear in a cubic way, but you have 4 local coordinates and you also have 4 basis states here because here you have this phi and phi, and in the action before here you get also psi square. So you still have 4 local coordinates, 4 basis states. So like it's cubic from the spacetime point of view, but not from the worldsheet. So now we can try to introduce new vertices, W2 and 3, in this way. And now the point that, okay, if A2 were living not in 2 copies of the Hilbert space, but in 1, you would get something very close to this V3 prime vertex you find in the proof of background independence from Sonoda and Zwiebach. And in particular, you can show that steering these vertices reproduce the boundary of V4. So now the point that it tells you that if you find a new propagator which is non-dynamical, you could have a chance to cover the vertex region. But I didn't manage to find such a form yet. So it's still an open question how you really do this, either like in a constructive way, or if you just try to guess the correct propagator. Now for the worldsheet, so we insert this tensor product states at different punctures. Now the question is that can we try to bring them together, for example, using OPE? Do we have singularity or whatever? And in terms of worldsheet, we have some diagram like this. So you see that here you have psi and psi. And here you have some place where you have a sigma, and you must insert sigma at the same time on the 2 punctures. And the propagator will need to define some local coordinate patch on 2 punctures, and then you can go this to another place with 2 punctures. So it's really a generalization of what you do in normal string theory with a plumbing fixture where you glue 1 puncture to 1 puncture. Now you have 2 of them. If you were able to bring them together and just describe everything with 1 punctures, like on this figure, then you would solve your problem and you could really claim that the theory is cubic. Also because this kind of surface with only 3 points are very easy to describe in string theory, but with 4 points, it is not. So again, it's an open question. If anyone has some ideas, I'm happy to discuss more. But for me, it looks like you should be able to define something like this for the worldsheet. So here are some questions for the generalization. So how we can generalize this to higher order? Because we get a product with more and more outputs. M2 has 2 inputs and 2 outputs, so it's not an infinity product. And so we need to find a structure for the action. So because if we find the symmetry and the structure, maybe we can just write the action and then try to gauge fix and reproduce the old action instead of doing it by trial and errors. And it happened that there is a homotopy algebra which is called IBA infinity, which possesses all these properties. Okay, so I will not go into the details because it starts to get technical, but the main idea of IBA infinity is that you introduce a tower of product where you take M states and you get N states, which can live in tensor products. So, like the coefficient can be really general, like the sigma, RS, K1, K2, like we saw before. So L infinity, you get M to 1. Here you get M to N. So it's something more general. You have a generalization of the L infinity relations. This induces also a BV algebra. So you know that if your action has this structure, you also it's also a well-defined quantum theory. Now the string field, in fact, you will get a string field which is not just in H, but we get string field for all tensor product of H. And so as we saw, sigma is in 2 copies of H. So it looks not exactly what you need to write the action. Okay, so you have a formal way to write the action. So now what we could do is to start with this, try to explain and try to see if we can match like the more like trial and error action I wrote before. We have equation of motion and so on. Gauge invariance with again the gauge parameters live in n copies of H. And we can try this at the quantum level. So as you see, there is a structure. The question is how you match to the real string theory we know, and how we give a broadsheet interpretation to all of this. Now I'll finish with my three conjectures. So the first is that we can rewrite this L infinity closed string field theory as a IBL infinity string field theory, and both are equivalent on shell. The second is that maybe you can rewrite this theory as a vector infinity algebra. So instead of looking at IBL, we just package this as a vectors of string fields. And finally, there is a parameterization so that the action is cubic in the field. Okay, so I think given the strictification theorem, there is a good luck that all of this should work. But for now, it's still very hypothetical. So let's see what happens in the future. Okay, so here I said. So conclusion. So first, with all like this toy models and ideas on clustering field theory, like we have we way forward to try to get a cubic clustering field theory, which also has a homotopy algebra. So it means that like in general, every string field theory which worked well had such an algebra. So it's definitely very valuable to be able to write this in this formalism. And it's also the first time we get an algebraic description of string field theory with auxiliary fields, where you can make manifest as homotopy algebra. So what's next? So a first step would be to study other toy models, in particular like SL2R, open bosonic SFT. So first trying to write the quartic term and make it cubic again. Another would be to work with the Munich open superstring field theory and also look at the quartic term and try to make it cubic, and then maybe change to higher order, maybe find some pattern and so on. And when we have done this, we can move to closed string field theory, and the hope would be able to do an explicit computation of vertices and amplitude, find classical solution, for example, using truncations, and maybe study thermal effects from mean field theory. And I will thank you for your attention.
Are there any questions?
I was going to ask, did you read Sen's paper about parentizing 2B supergravity? Because he uses arguments from string field theory to introduce an auxiliary field, which he argues has no propagating modes, but it's needed for the construction. Is this related to this one, or is it different? Completely?
It's a bit different. So the overall idea is saying that, okay, I have some constraints. I want to lift it, so I will enlarge the Hilbert space. It's the same. So this indeed gave me some inspiration for this kind of work. The main difference is that in this paper on supergravity, you have a constraint on the fields, which is imposed on the side of the action. And so what you want is to bring this back in the action, but for this, you just need a bigger space because you need to introduce. So basically, if you impose this constraint in the action, you get a degenerate matrix for the kinetic term. So you want to work in a space where this matrix is not degenerate, so you just make everything bigger. So this, what he did for superiority, you also do it in string field theory for the Raman sector, which is basically what gives you the C field in supergravity. You can also redo it to remove the level matching in string theory. I don't know if you're familiar with it, but it's something else. But here, indeed, it's a bit different. It's with constraint on the side which you want to get in the action. In my case, it's more like just shuffling things around. And I know that I can just rewrite the interaction with auxiliary field. So it's a different type. The second thing which shows that it's a bit different, that in my case, it's proper auxiliary fields. When you work with S constraints, what happen is that you need auxiliary fields, which are, they're better called spurious, because they don't have dynamics, but they still have free states which propagate. So they are not exactly auxiliary in that case. It's also another difference between the two cases.
Okay, thank you.
Right. Looks like
Oh, one more question. So for the I saw in your paper that you said that the tachyon solution that there was a mismatch, and you had this exponential divergence away from the tension, matching the tension to the tachyon vacuum solution. Is that just because there's no non-perturbative stuff anymore? And is it like could you hypothetically get it from taking some nice limit of the cutoff, or is it But because it's kind of like it's kind of like seems that the low energy theory is still cubic open string field theory, right? Which kind of should contain the tachyon vacuum stuff, the tachyon condensation stuff, right? Or
yes. So what happened? So you mean in this paper on the stubs, right? This Yes. So here what happened that we in the section where we look at the scalar field, we just look at so we do a truncation of the action to the cubic sector. And the point that when you do this, you are missing a lot of fields at higher orders. And what I think is that when you get this mismatch is because the fields you lose when you do this truncation are not exactly the same. So you are missing some contributions. So if you were working with a full string field, then I think you would just find again the tachyon vacuum. And if I'm correct, there is a Georg Stettinger who wrote a paper quite recently where he studies this open string field theory with stubs and how you can map classical solutions from, with and without stubs. And here, so I forgot the conclusion of the paper, but it's related to what you're asking. And another paper which studies this question about like the effective potential when you truncate and so on is from Atakan and Ted Erler, where they also study a bit like this contributions. So to summarize it, in our paper, we just did a brutal truncations, and it's why we see a mismatch.
Okay, thank you. Very helpful.
So if there are no more questions, let's thank our speaker once again.
Thanks a lot again for the invitation. Let me say again that if anyone wants to discuss on this or have question later or anything, don't hesitate to drop me an email and we can meet again on Zoom and so on.
All right. Thank you so much for taking the time. And I think one or two of us will probably reach out to you with questions.
Thanks a lot again. Have a good day.
Bye-bye.
Bye.